Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about how to design two-channel relay module using a opto-coupler. This is the 6th tutorial of practice projects for PCB designers. I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder. In this tutorial, I am going to give you a block diagram analysis of a two-channel relay module and then a schematic design using EasyEDA tool. Now in this particular frame or in this particular view, you can see that there is a one relay module, which is a classic relay module. Another one is a solid state relay module. These both are different, they are not same, and their application and behavior and functionalities are completely different. However, just for the sake of your understanding and to know or make you sure that you are designing this relay module, I have added these two images. Do understand, when you are using an opto-coupler and designing some circuit, then this kind of a relay module is what we are going to design, not the SSR based solid state relay module. Now let's jump into the black box analysis for the two-channel relay module. This black box is for the single channel. Of course, we are using the replica of the same thing for the another channel relay module as well. First of all, we will be having an input connector where we will get the 5 volt input signal along with a control signal which will turn on and turn off the specific relay. The control signal will be given to the opto-coupler circuit, which will be controlling the transistor as a driver, which will turn on and turn off the relay coil. The coil will be provided with the plus 5 volt DC connected to the input connector from the external source. And this relay is having a COM point, NO point and NC point, which eventually stands for normally closed, normally open and common point for the signal. The output signal, a switching signal connector, helps us to connect the switching voltages, maybe a AC voltage, DC voltage, low voltage, high voltage, doesn't matter. It really switches anything that you connect to the signal point where we can switch the signal, which is a relay point. But do remember, the maximum power that a relay module can switch is noted on the relay module or the relay part number. You can see here, there is a voltage and current rating given on this particular image, which is not so clear, but I hope you understand the point here. So every component has its own maximum current rating and a minimum current rating. So to understand that particular thing before connecting any voltage to the relay module, that's what the black box analysis of the two-channel relay module. This is a single channel one, same replica for the another channel as well. Now we'll go to the white box analysis. Again, I'm not jumping on the morphological chart. Why? Because I believe you guys are now very familiar with the morphological chart and you do it by yourself. If you do it by yourself, you will learn how exactly the morphological chart works in the industry. So I recommend you to compute or do the morphological chart for the opto-coupler, transistor, relay module or the relay IC or the device that we are using and the connectors as well. Now, after doing a bit of morphological chart and with my experience, I came up with the Berg header for the input connector where we will be connecting a power, which is a 5 volt and a ground, and along with the signal, a control signal for both the relay channel. And 817 IC or 817C is the opto-coupler IC that we are using in this particular example. BC547 is the N-channel NPN transistor. It's a NPN transistor, not N-channel, because it's not a MOSFET, it is a BJT. So NPN transistor, which is used for switching the relay. And the relay that we are using is a 5 volt relay because we are having a 5 volt input here. So it is the part number for this relay is a SRD05VDC. And the terminal block we are using is 10 ampere of a current rating and it's a T block, terminal block with a 5.08 pitch. This is how our white box analysis looks like for the entire two-channel relay module. Again, this is a single channel, a replica for the another channel as well. Now this is how the circuit diagram looks like. This is completely an online circuit diagram. I referred it from the Google and it is a very good reference that I have selected. That's the reason I have selected this one. You can see here there is a VCC, which is a special VCC pin connected to the relay directly, or if you are having a specific VCC signal coming from the connector, a Berg header, then you can jump that one to the relay module as well. And there is a freewheeling diode to avoid the glitches in the relay or avoid the EMF effect on the relay module. And then we have opto-coupler circuit, which will turn on and turn off the relay by using a transistor as a driver here. And the transistor is driven by the base terminal with a small resistor with the opto-coupler output, and the ground pin is common between all of them. And then we have a NO pin and NC pin and a COM pin, which is connected to the terminal connector at the output side, which is useful for the connecting any signal that you want to switch from this particular relay module. This is again a single channel relay module circuit. We are going to use the same circuit for making another channel, so that in one PCB we'll be having a 2-channel relay module. This is how the entire circuit diagram looks like. Now let's jump into the design activity. Here we have our ECEDA tool. Now I'm going to go to the file section, go to the new section and create a new project. The name for this one is 2-channel relay module. Oops, I have forgot to add underscore, so let's add that one. So it's a 2-channel relay module, right? So I'm going to click on the save option and start with the same activity that we did in our previous tutorial likewise. All right, now you can see that this is how the schematic of two-channel relay module is to be done. In fact, in this, you have noticed some unique feature of Easy EDA tool. That one is if you want to create a same circuit once again or a little bit modification in that as well, you just need to select the entire component or entire circuit diagram and then just hit the Control C and Control V on your keyboard. That is copy and paste basically. And you notice that it is not just about the copy pasting the circuit. You can also notice that the designators are upgraded by default. Why? Because the reason is if you can see there is a R5 in this particular circuit, then the next designator R6 is located for the first element in the entire circuit. The copy paste function works absolutely fine in this particular tool. That will reduce a lot of time for recreating the same circuit once again. That's why in my entire tutorial, I have given you only one circuit block diagram analysis, one circuit white box analysis, and then only one circuit diagram that I discussed. Why? Because in our Easy EDA tool, it is quite easy for replicating the same circuit once again. So that is how I replicated the relay 2 circuit as well as the connector for the relay 2 as well. I just need to change these labels and the custom words that I have given for the circuit components. But other than that, there is nothing which is completely updated by itself while copy pasting it. Notice here, I'm using these kind of a connector. You can see them as a net port. Instead of using a label, I'm using a net port, which is much more better and much more represented in this entire EDA tool, which is Easy EDA. You can use the net label as well. There is nothing wrong in that, but I'm prefer to use these net port rather than using a net label. Net labels are more suitable for the digital circuits and all. Net ports are suitable for the hierarchical design. However, this is not a hierarchical design. This is very simple, very straightforward. Though it is straightforward, simple, better to use the net port rather than using a net label. This is all about our schematic. Now let's jump into the PCB layout design and see how we can make the PCB layout of the same one. All right, now we are done with the two-channel relay module PCB designing as well. This PCB is done in a very quick way, so there are some problems which we have to solve. But anyway, this is very best and very suitable for the beginners who are practicing the PCB designing. This is a single layer PCB designing. That's why you can see a lot of routings within the IC and all. That's absolutely right one, and IPC standards always are followed in this single layer PCB designing. Only one thing that I have not followed here is we need to add a creepage clearance here. The creepage clearance is the concept which we literally create a slit in this particular PCB, like how we have a border edge here. The same way, by using a board outline, by using a wire tool, we literally create a slit like this here. Which you might seen in real-time PCBs and all, right? So these slits which are provided here will isolate the entire DC circuit from the AC signal that we are switching by using a relay module, which I have not done here because of the track here. Beneath that there is one track, and to avoid that there is other complexation, like we need to bring this transistor here and we need to adjust the diode a little bit, and then we need to add a creepage clearance. The concept of creepage clearance is essential and very important when you are dealing with high voltage signal switching and all that thing with respect to digital circuitry and all. But this one is a practice project. This one is a simple practice project for the beginners. That's why I'm not going to deal with the creepage clearance. But do remember, after completing this PCB, give a try to keep this transistor beside this diode and adjust this diode to exactly the edge of the relay module, and then add a creepage clearance just before I shown to you, right? Just give a try on that. If it is possible, then that is absolutely a great skill that you have to learn when you are dealing with the AC signal and DC signal design activity, especially with respect to switching signals in the entire circuit. And other than that, I have added a NO, NC and COM pin indication at the output level, and also added the relay 1 and relay 2 indication at the input side. VCC is connected. The one important thing that you have to learn in this is using this triangle. The reason why we added this triangle is, if I remove that, you can see that there is a 90 degrees created here. This 90 degree will cause a problem in case of a fabrication. This is called acid trap actually. When you are doing a ferric chloride based acid etching process with respect to the PCB, because of a sharp corner here, because of a 90 degree, the proper PCB etching cannot be done here. That's why in PCB designing, people always do a routing with respect to 45 degree angle, not with a 90 degree. The reason is acid trap is a concept. Do remember this one. This is a very good question with respect to the interview perspective. If you are interested to know about that, Google about it. There is a good information about it. But right now you can understand, we do not create, or we should not create a 90 degree in any track. That's why we introduced one triangle here. Again, this triangle can be placed however we want it. The best way is using this particular solid region and drawing the triangle as per our convenience. There is no specific placement and specific dimension for that. You can increase the length, increase the width, whatever you want to do it. Make sure that it is a 45 degree, at least not a 90 degree. There should not be any sharp edges on the triangle as well. The purpose of adding a triangle is to remove the sharp corners. If you create another sharp corner, then what is the use of that, right? So make sure that you use the triangle feature as well. I have used it twice, here once, and the second one is here. And after that, I have spoke about the creepage clearance concept. And notice very important thing. This particular COM pin track is a 2 mm or 2.5 mm. As big as possible, that is the best one. If you can do it more than 2.5 mm, that is absolutely recommended. If not possible, then it's okay. Go with a 2.5 mm at least. And notice this track is exactly straight. There is no bend in this particular track. And even with respect to this one also, there is only one bend here. Other than that, it is inevitable. So that's why we have added one bend here. Other than that, it is absolutely straightforward. No curvy feature and no much of routing there and here and putting the connector somewhere else. Why? Because this is a high voltage AC signal. I believe that most of the people use a relay module for switching the high voltage AC signal. And high voltage AC signal will be having a 50 Hz of frequency. If you keep this track running anywhere in the entire circuit and coming back to the connector, then it will damage, or it will disturb, and it will interfere with the functionalities of the digital circuit, and it may cause the severe damage to the component, which is irrecoverable. In worst case scenario, if anything goes wrong with respect to AC section, that will propagate the signal to the microcontroller connected to the relay 1 and relay 2. That will damage your entire microcontroller straight away. So that's why it is always better to isolate the AC section or AC section with respect to the DC section by adding a one isolation point here, which we have not done in this. Again, since it is a beginner tutorial, I don't want to put up a lot of component or a lot of learning points in the single video. That's why. So make sure that you at least follow the same circuit design or the PCB track method that I have shown in this particular video. Again, other than that, you can explore with the different placement component activity and playing around with the transistor as we discussed, and also try with the creepage clearance. This is how our the two-channel relay module looks like. And if I go for the 2D diagram, this is how it looks like on the top side. And if I make it to the green color, this is how it looks like. And on the bottom side, this is how it looks like. Again, this is a single layer, not even a single jumper is used in this entire circuit, and all the tracks are following the IPC standard, not using a 90 degree anywhere. If I have created a 90 degree, then I have solved it by using a triangle solid region. And then if I go to the 3D model, you can see that this is how the 3D model looks like. Pretty awesome. We have got this 3D model for the relay as well. I think pretty every component is having a 3D model. Oh, that's a great one actually. Even opto-couplers are loaded in the 3D model. By default, they are there. So this is how the entire circuit looks like, two-channel relay module made by linked frequency. Again, this one is using a through-hole technology, and this one is much larger, much bigger size than the one available in the market. However, this is our practice project, so I want you to know about how exactly the relay modules are designed. That is the purpose. So maintaining the silk layer, maintaining the IPC standard, maintaining the placement of the component, that's the reason. That's why we created this entire project. I hope you have done this entire project the same way how we done right now in front of you. And I believe you understood everything. If not, if you have any questions, small question, big question, do not hesitate. Post it on the comment section. I'm very happy to answer those questions as per my schedule, whenever I'm possible to answer it as soon as possible. Okay. So thank you so much for watching this video, guys. See you again in the next video. Until then, make sure that you practice this particular project with a different iteration as we discussed in this tutorial. So consider subscribing to our channel Linked Frequency. See you again in the next video. Until then, tune yourself to make a difference.